Okay, that was 15.3. Basically, the line integral of a conservative vector field over a curve is independent of path. So what that means, and we could draw a picture. It's probably get in trouble for drawing a picture, but so imagine this space is populated by some sort of vector field. Um, so in other words, there's all kinds of little vectors all over the place in space, like little um, wind elements or something like that. And then you're integrating, you're doing a line integral over some curve. So I'm trying to look for a nice color here. Make this a pretty picture. All my cool colors are gone for some reason. But okay, so maybe I'm trying to find the line integral of the vector field over this curve, and curve's kind of just doing something crazy, you know. Now maybe it ends right here in the xy plane. What this theorem is going to allow you to do is kind of bypass having to worry about finding that incredibly complicated vector valued function, which represents that curve right there. Okay, so instead of doing all of that crazy business, you can kind of just go, you know, the quickest way between 2 points is a straight line sort of idea, right? So instead of all that crazy business, you're just gonna, you know, you could start here and then go straight to here and be done with it, right? So that's the idea. If you could show that something is conservative, then it's independent of path, and you could choose whatever path you want. Also, something that comes out of this is the closed curves. If you have some sort of closed curve in a vector field. So maybe I have to draw another XYZ plane over here or something. If you have a closed curve in here, because it's only dependent on one point, right? So if you have this point here as your starting place, and then you're just zipping up and coming back around to it or something like that, it won't, the line integral of this vector field over this curve will be equal to 0. Because basically what you're doing is just evaluating this point, and then you're going to subtract this point. And we'll see that here in a second. How do I evaluate that? We're going to need this thing called the fundamental theorem of line integrals, right, which is like the fundamental theorem of calculus. Okay. Okay, so that's the idea. Let's sort of dive in there and try to chug it out and see what happens. So the first thing, as promised, the fundamental theorem of line integrals. And this is with regards to vector fields. So what it says is, and we have some conditions as usual. We're going to be given some vector valued function for the curve. And then your vector field, which you usually represent with MNP, and just two variables, it'll just be MN. And And the vector field has to be conservative. And I forgot to let the t values, and the t value, let's say it goes in between a and b. So if you're given all that information, you can conclude the line integral of the vector field over the curve C is equal to the potential function evaluated at the endpoint, so x of b, comma, y of b, minus f of x of a, comma, y of a. So basically all you have to do is evaluate it here, and then, or this was a starting point, I think, when I drew it. So all you have to do is evaluate it here, and then evaluate it here, and subtract. And that's why if you have a closed loop and your vector field is conservative, you'll just get 0, because in that case, this is going to be the same point here and here, and when you subtract it, you'll just get 0. Okay. So anyways, we want to show you the proof of this, and also noting this little f, where did it come from? Little f is just well, big F is the gradient of little f. So f, we said, is a potential function, but in notation-wise, it's the gradient of the vector field. Good. Okay, so let's go ahead and prove this thing. And the crux of it, the key to proving it, is the chain rule from way back when. In particular, maybe I should just sort of extract it and talk about it a little bit here. So my stupid webcam's all messed up. Sorry, I'm going to adjust it every time now. All right. Right. So basically, we have eventually we're going to have this function of x and y, but x and y are dependent on t. So it's a x is some function of t. So how do we do this? We call so let's just say f of x of t, comma, y of t is our function. If we take the derivative of that, derivative of f with respect to t, how did that work by the chain rule? Well, we have to take the partial of f with respect to x, and then multiply that by the derivative of x with respect to t, and then plus the partial of f with respect to y times the derivative of y with respect to t. It's that idea that gets the job done for us here in proving the fundamental theorem of line integrals. Okay, so let's get at it then. Proof, in case I didn't note that already. Suppose our vector field f is conservative. Then the gradient of f is going to be this potential function that gives you the vector field. Okay? And so what is that? Well, that's just going to be sorry, so I shouldn't say the gradient f, right? It's f is literally just equal to the gradient of the potential function, and that's going to be equal to the partial derivative of f with respect to x, comma, the partial derivative of f with respect to y. Okay, so you kind of already see the bits and pieces that are popping up. So note then our line integral for the vector field over the curve C, f dot dr. remind yourself that this dr element, we can rewrite that. So it's f dot dr with respect to t times dt. Sort of abusing the notation. This is the dot product, and then this is just times dt. Right. So you would be given this r function somewhere. So suppose f is conservative, but you're also given r of t is equal to x of t comma y of t. And that's the curve you're integrating over. So this part and this part you can rewrite, right? You can rewrite the, sorry, you can rewrite this part and this part. You can rewrite the vector field with the vector for the potential function, or the gradient of the potential function, which is df over dx, comma, partial of f with respect to y. And then you could rewrite this part by just taking the derivative of the components of that thing. So that would be the derivative of x with respect to t. Usually we just put x prime, right? But this will make it much more clear that what we're ending up with is just the derivative of f with respect to t. So the partial derivative of x with respect to t, partial derivative of y with respect to t, and then dt. Then if you dot product those things, you get exactly this thing here. So let's just take a look at that. So this will equal the integral of the partial of f with respect to x times the derivative of x with respect to t, plus the partial of f with respect to y times the derivative of y with respect to t, and all this dt. Okay. But then we could just replace this entire thing with this, because that is just the result of doing a chain rule when you do the derivative of f with respect to t. Right? So this whole mess in here becomes then the derivative of f with respect to t, and then dt, integrate from a to b. And then from the fundamental theorem of calculus, you could just kind of say the integral of a derivative, you get back to where you started, kind of like inverses. And this, the book, so the book is going to call that the Net Change Theorem. And if you took Calc 1, you've probably forgotten about it, and you haven't thought about it in a year. But it's in there if you want to look it up. Anyways, what you end up with then is just the potential function evaluated at b. So this would be x of b, comma y of b, and then minus the potential function evaluated at a. Okay, and that's the fundamental theorem of line integrals. Okay, the only restriction is that you actually have to have a conservative function to pull this off. Anyways, let's go ahead and dive right in, and start looking at applying this to certain problems. So, for instance, 25. Let's take a look at that guy. So we want the line integral of this vector field. Okay, and we're integrating over the curve from 0, 0 to 3, 8. Okay, so the point the point is now I don't have to really figure out the vector valued function that represents the line from here to here or anything like that. Don't need that anymore. If you want, you can instead. I mean, you can still do it that way, but if you want instead, you can now show that this vector field is conservative, and this is the vector field here. So this thing, as crazy as it looks, is the vector field. You'd have to show it's conservative, so you need to do the partial with respect to y of 3y, which is equal to 3, and show that equals the partial with respect to x of 3x, which of course is also 3. So that thing is conservative, and then you just need to get the the potential function for it. So remember, you need to kind of integrate with this respect to x. That'll sort of give you the potential function, but you need to solve out for the constant parts. So you take the derivative with respect to y and set it equal to this. So what did that look like? That's the partial with respect to y of the integral of 3y with respect to x, and that thing should equal 3x, right? So then go at it. So this is 3xy plus whatever was sent to 0 by the derivative with respect to x. So that would be some function of y. And so I have to take the partial with respect to y of that, and that should equal 3x. And then partial with respect to y of that is 3 x plus g prime of y equals 3x. And then you could subtract 3x from both sides. G prime of y equals 0. Integrate both sides, and g of y equals k. And then your final answer is, it's sitting right here. You just have to take this part of it and plop it into that formula. Oops, sort of fell off there. And that's your potential function. Okay, so my potential function f of x comma y is 3xy plus k. The constant won't matter because you're taking a difference. So, you'll have, in this case, we don't need the t value here because this is what it is at t. We don't really care what the t value is, just so long as the t would give us these numbers. So I'm not worried about something like that. But the actual integral ultimately then is just going to be this thing evaluated at these points, right? And you have to take the difference. So it's f of 3, 8 minus f of 0, 0. And you just plug that stuff into here. So 3 times 3 times 8 is 72. And then minus 3 times 0 times 0. And then again, there's that k stuff in there. But if you think about it, what is that going to do? It's going to be 72 plus k minus 0 plus k. And the k's will just cancel out. Okay? So you'll get 72 plus k minus k, which of course is 72. So whenever I evaluate these things, I just kind of completely disregard the constant part, right? Alrighty then. Let's do another one. And this time the line integral is given in a differential form. Can't get these two pieces of paper apart. I apologize. There it goes. 27. So the integral of cosine x sine y minus dx. So it's a differential form. Minus sine x cosine y dy. And I'm integrating from 0 to negative pi, and then to 3 pi over 2, comma pi over 2. So that's the curve that I'm worried about. Okay, so first I'm going to show it's a potential function. It's conservative. So take the derivative of the first guy with respect to y. And of course that's just cosine x cosine y. And then take the derivative of the second guy with respect to x. Whoops, this should be a plus. Otherwise, it's not going to be conservative, is it? So that will be cosine x cosine y. And of course, those are equal to each other, so it's conservative. So we can get the potential function and go on from there. All right, so let's do that. I'll take the partial with respect to y of the integral of cosine x sine y with respect to x, and set that equal to sine x cosine y. So if you're wondering, this is your m, and this thing is your n. Okay? The thing with the dx is the m, and the thing with the dy is the n in your vector valued in your vector field. Okay, so this would be m comma n. Okay. All right. So let's go ahead and get the potential function. With respect to x, I'm just integrating the cosine x part. So that would be sine x, sine y, and then plus whatever would be annihilated by the derivative with respect to x. So that would be some function of y. And then on the other side, you just can bring down the sine x cosine y, and then take the partial. So the partial with respect to y is going to be sine x times cosine y plus g prime of y. Okay. And then move this over and set, you got g prime of y is equal to 0. So integrate both sides, and you get g of y is equal to some constant k. So therefore, our potential function is just going to be f of x comma y equals sine x sine y plus a constant. Okay, so I can evaluate the integral just by putting these points into that function. So the integral, the line integral of this vector field would equal this thing evaluated at 3 pi over 2 pi over 2. So sine of 3 pi over 2 stupid computers being a jerk. Sine of 3 pi over 2 cosine of, now I'm just totally lost. Sine of 3 pi over 2 sine of pi over 2 minus sine of 0. My computer's just flipping out. It needs me to restart it. Oh my gosh. Yeah. Times sine of negative pi. Okay, so evaluate these things. Sine of 3 pi over 2 is negative 1. Sine of pi over 2 is 1. Sine of 0 is 0. Sine of negative pi is 0. So you just end up with negative 1 for your answer. Okay, so the great thing about this is it's going to give you ultimately now we have 3 different ways to integrate a line integral of a vector field. You can parameterize the thing. You can find the potential function just like we've been doing. But also now you can take alternative paths. Okay, so what I was saying at the beginning of my lecture is that supposing you do have something that's conservative, then it's independent of whatever path you take, because all we're doing is evaluating at the endpoints. Okay, so sometimes they'll give you so let's call this independence of path, I guess. I don't know what number I'm on, but we'll call it number 2. No, it's number 3. Okay, so number 3, path independence. So an example, I guess the example, it used to be example 5 in the book. Find the line integral of the vector field of f over the curve C, where the vector field is y cubed plus 1, and then 3x squared, so 3xy squared plus 1. And the curve is this weird semicircular path from here to here. Okay, so from 0, 0 to 2, 0. Okay. And so let's say, for instance, maybe you've forgotten how to get the vector Phi equation for a circle that's not, especially one that's not centered at the origin, right? That may be a little bit of work, maybe a bridge too far, right? So never fear. All you have to do is, instead of going on this path, you can go directly from here to here and just say, well, I'm going to do this instead. And so long as it's conservative, you can do that. Okay, so do this path instead. Okay. Okay, so let's make sure it's conservative, and then we can pull this off, right? So the partial with respect to y of the m component, y cubed plus 1, is 3y squared. And then the partial with respect to x of 3xy squared plus 1 is 3y squared. Those are equal, so it's conservative, so you need not worry about finding the parameterization of this weird curvy thing. You could just work with this, which is a lot easier, right? We all, hopefully by now, know the vector Phi equation for a line. So you just go 2 minus 0 is 2, and then 0 minus 0, 0, t, plus your starting point, which in this case is 0, 0. And we're varying the parameter from 0 to 1. And then we can simplify this thing into 2t comma 0. Okay. All right, so I'm not going to get the potential function. I'm just going to do it via parameterization. So I have this line integral of the vector field f dot dr over the curve C. And I can rewrite it. It's just going to be the integral of f, which is y cubed plus 1, but I'm going to reparameterize it with this thing, right? So instead of y cubed, it's 0 cubed plus 1, so that's just 1. And then I'll have 3 times x, which is 2t, times y squared, which is 0, so this will be 0 plus 1 again. So the vector field along that curve is just 1, 1. And then I'll dot it with the derivative of r. So r prime of t is equal to 2 comma 0. So 2 comma 0, and then dt. And of course, you know, what is that? It's just 2 plus 0, so that's 2 dt. And integral of that is 2t, and I'm evaluating from 0 to 1. So that's just equal to 2. So a little bit easier. And on top of that, then, if you're ever on a closed loop, you need not do anything, right? You can just say it's equal to 0. So you can make that as crazy as you want. And okay. Anyways, we want to sort of see the proof that the proof of the following theorem, and there's probably more theorems in the book. I'm not hitting them all. This is the most annoying one. The fact that let's see where it is in my notes. It's theorem 15.6. So if apparently it says if the vector field is continuous, and it seems like that's not right, but I'm pretty sure. It seems like maybe it's like the mixed partials are continuous or something. Ugh. I gotta look at the stupid book. Hold on. All right. No, it's just. I don't know what it is. Yeah, so f is continuous. All right, that's fine. trust myself a little more. All right. F is continuous, then what? Well, F being conservative will imply that the line integral of the vector field over the curve C is independent of path. Okay, and this is clear because the fundamental theorem of line integrals say if the vector field is conservative, then all you have to do is evaluate the potential function at the endpoints. So it don't really matter the path, right? So that's clear. The other direction, not so clear. So if something is independent of path, then it implies that F is conservative. Okay, so we want to prove that other direction. So if F is independent of path, then it's conservative. Okay, all right. So how does this work? Well, we have the book is going to throw some suppositions at you. So of course we're supposing F is continuous. What else are we supposing? It's independent of path. This line integral is independent of path. Let's sort of instantiate the vector field. Let's call it Mn. And then we need a picture here. So we're in some region, I guess, where this F is continuous, and we're going to consider this kind of diagram here. There's going to be two parts of this. Okay, so we need two paths, but the first version of this, we have this path C1, and then this other path C2, and C2 is supposed to be horizontal. Okay, so I'm starting at x0, y0, and then I'm going to this point here, which is x1, y, and then this point here is x, y. Okay. So what? Okay. If I can find a potential function such that the gradient of that potential function is equal to this vector field, I think I'll kind of prove it. Okay, and that's, I don't know if my proof is going to be as good as the book, but that's kind of how I think of it. All right. So if nothing else, this will give you an idea. Maybe I should have put a sketch of proof, but it's pretty close to the proof. Okay. Right. So I claim that the potential function is basically just the line integral. Okay. It's kind of weird, but that's what I claim. So I'm going to say claim the potential function f of xy is equal to the line integral of this vector field over this curve here. Okay, so this curve right here. Okay, so if this is then the potential function, if I take the derivative with respect to x, I should get m, right? Okay, so that's what we kind of do. Right, so I'm going to rewrite this line integral as in its differential form, and hopefully that may be a little easier to stomach. Okay, so I take f of xy, which is going from x0, y0 to xy. Okay, and I'm going to break it into two parts. So f of xy will equal the line integral. and I'm going to put it in differential form at the same time. Okay, so this will be the C1 part of m dx plus n dy, and then plus the C2 part of m dx plus n dy. Okay, and then I want to take the partial derivative of this thing with respect to x, right? So the partial with respect to x of f of x comma y equals the partial of this thing with respect to x. Okay, okay, so one thing to note here is what this thing means. The line integral over this curve, okay, it's independent of path, so it really only it's depending on the long story short, it is you kind of pretend that this, I'm sorry, I'm struggling so much. You can't pretend that this thing is literally as it reads. It's a function of x and y. So this thing is populated by all kinds of x's and y's. And in particular, this function is going from here to here, okay? So as an abstract function, if I went from here to here, I would be kind of inputting, instead of x and y, I'd be putting x1 comma y into here, and that would give me sort of my answer for the line integral of this part. When I do that, I'm replacing all of the x's with x1, okay, which is a constant. And the result is that this function, when I put in x1, everything in here that had an x in it will be just a constant, and all I'll be left with is a function of y. Okay, so this entire first part of the integral going from here to here, which you can think of as, so this thing here you can think of as f of x1 comma y. Okay? So this function f of xy represents basically, I don't know, a line integral from x0 comma y0 to x comma y, right? So to figure out the line integral from x0, y0 to this point here, what you're doing is plugging in x1y in for xy, right? And then what I'm saying is that when you do that, you're essentially getting rid of all the x's. You're replacing it with this constant x1. Right? And then what that forces this thing to turn into is a function of just y alone. Whatever the heck it is, I don't know. But it doesn't really matter because whatever function of y it is, if you take the derivative with respect to x now, that thing will just turn into 0. Okay. Hopefully that's somewhat clear. Then this thing right here, I'm not going to worry about it in terms of the potential function. I can just kind of, I think I could just look at it as is, right? So partial of this with respect to x of this line integral over the curve C2 of m dx plus n dy. Okay, and then for this part, that's why I chose this horizontal line right here, because the change in y over this curve is 0. Okay? So you know, you can even imagine doing a parametric parameterization of this horizontal line with a vector value function, and the y component is you know, 0, because it's, you know, 0 minus y is 0. So this part is going to be 0 in this part of the line integral, because of the way we chose that line. All right, so anyways then, what happens here then, this with partial with respect to x of this part of it would just be 0, and then you're left with the partial with respect to x of the line integral or at least this part of the differential form of the line integral over C2 of m dx. Okay. And m is just the partial of, well, what the heck is this thing? It's long story short, it'll turn into m, okay? So at the end of the day, it's just going to be m. Okay, so I've kind of done it. You know, I feel like I'm missing some pieces and parts. You go read the proof in the book and kind of piece it together. But that's the idea. Okay. So that's half of it, right? Because the ultimate, you know, the ultimate big picture here is to show that the partial derivative of this with respect to x is m, where m is the first component of our vector field, and then the partial derivative with respect to y is this n part, where the n is from the other component of the vector field. So let's do the other version as well, really quick, to just give you a flavor of it. And in this case, you have to do a vertical line. Okay, so you're gonna kind of move from here to here. That will be your new C1. Whoops, sorry. So you're going to go from here to here. That would be your new C1. And this point right here is going to be x comma y1. And then you have a vertical line, which is going to be your new C2. Okay. So we'll kind of do the same spiel. And we should get our other guy popping up. So yeah, so f of x, y in that case will equal the line integral, this guy, c1 m dx plus m dy, and then plus the line integrals over c2 of m dx plus m dy. Okay. And again, we want to take the partial derivative now with respect to y and show that's equal to m. Okay, so the partial derivative with respect to y of this thing and this thing and this thing and this thing. Okay. All right, so let me get a different colored pen. So this thing right here, in this particular case, you can think of it as f of x comma y1, right? Because it's the integral over this curve where that means just input x comma y1 into this function. And what's happening there is you're replacing all the variable y's with this y1 constant, and it's a function in terms of x. Okay, so that'll equal the partial derivative with respect to y of some function in terms of x, and then plus this thing, okay? And in this case, this thing right here is 0 because the change in x as you go from this point to this point is 0. So you get a big 0 there, and you're just ending with the integral of n dy, and we're taking the partial of derivative of that with respect to x. Or sorry, with respect to y. No, with respect to x. We should be doing, no, it is with respect to y. I apologize. Okay, there we go. Right. So this part will be 0, and then for some reason my brain isn't processing this. It should be just n. I presume it's one of those fundamental theorem of calculus things, the derivative of an integral that kind of cancel each other out type deal. Yeah, because this is a function of y, then you're kind of taking the derivative of it with y, with respect to y. Okay, so that would just be plus n, which equals n, which shows that the vector field is equal to the partial derivative with respect to x of this f function, comma, the partial derivative with respect to y of this f function, which is equal to the gradient of this f. So that means that thing is the potential function. Okay. That proof is probably one of the harder ones in the book. It is not easy for me to do, so I apologize if I was kind of struggling there on it. Okay. Let me do one example from the book, preferably one where we're kind of getting the potential function, and the potential function isn't a constant, doesn't have a constant thing attached to it. So let me see if I can find one. That's the hard part. It's like impossible to find one. It's like I did 5 of these in my notes, and every one of them, I think I can find an example. Sorry, just 1 second. Evaluating a line integral over a path. I need a vector field. And then getting the potential function off of it. And for the life of me, I just can't find one every time I try. Let's just do one at random, and hopefully it'll be, you know, something will work out for us. Forget it. I'm gonna spend a half hour looking for this stupid thing. I can't find it. I'm sorry. I'll shut up. All right. Well, if you have questions, just email me and I'll help you out. I'll walk you through it. Otherwise, I'll see you next time.